Jai to all. I am again here for data analytics and visualization. This is the fifth lecture that we are talking about in data analytics and visualization, and I have taken a complex topic of clustering with some examples which belongs to unit 4 of data analytics and visualization syllabus. So, if we talk it that ways, clustering and classification, we have discussed a lot about it. Clustering is an unsupervised means of learning, and wherein we are trying to find certain patterns within the data. Generally, it is used as a process of finding meaningful structures, explanatory underlying processes, generative features, and grouping inherents is a set of examples. Basically, what is happening opposite to supervised learning, in unsupervised learning, we do not have the classified data. It is the label that we get as an output. Instead of giving it as an input, as in classification, we get the labels as an output of the unsupervised learning or the clustering methods. Basically, how does this clustering happens? Clustering happens on the basis of similarity or dissimilarity. Dissimilarity of attributes and similarity of attributes. So, if the attributes are of similar kind, they will be clubbed together, clustered together, and the dissimilar will be moving out to far apart. So, we will see some examples of clustering and understand how it is happening. It's very much important as it determines intrinsic grouping among the unlabeled data. The key point is unlabeled data. Here we are handling unlabeled data, and that we are labeling the data as an outcome of this process. So, we are working on an unlabeled data, labeling it, identifying it, which are the similar type of data that have to move together and which are dissimilar type of data that have to move apart, and that is the whole purpose of clustering. The purpose of clustering can be finding representative for the homogeneous group. Yes, out of the whole cluster, you just want to find one representative, one representative data representing the whole of the cluster in itself, right? Then finding the natural clusters, describe the unknown properties. So, these properties are not known, but by the clustering, we are able to at least group them together and then label it, right? Then finding useful suitable groupings, useful data classes, or finding unusual data objects. If we have clustered all the data that is present, suppose in some cluster, but there may be certain points which are very far off and they are not able to be clustered in any of them. So, there may be certain situation that such a big cluster, or there may be one outlier lying altogether differently. We are not able to cluster it in either in this or this or this. And that is the situation of finding an outlier. Why do we need an outlier? We need to an outlier detection is required to see certain anomaly detection can be there, certain pattern, out of pattern transactions if it is happening, fraud detection, all this are the use cases where outlier detection is a boon. Then clustering methods can be either density based. There are 4 to 5 clustering methods that we will talk about. First is density based. These methods consider the cluster as the dense region. They are grouped together based on the density. So, the example of such density based spatial clustering, application with noise, optics, these are examples of clustering based methods. I am fast moving on these slides because I have to basically go on to the numerical, which is based on hierarchical clustering and k-means clustering. But these are basic classification, density based, where you group the clusters according to the density. The more denser, the closer the items, the denser the items, they belong to one group and other may belong to other group. So, what is the purpose of maintaining this density based? That the more which are dense together should be grouped together and the which are far away from each other should be put far away. So, ordering, these are the various algorithms behind it. DB scan is the most popular one and optics is another, which is density based. Then we can have hierarchical based clustering. So, I have got an example for you on the base of agglomerative clustering, HEC, I want to discuss in detail. So, that is hierarchical clustering, where the clusters formed in this method form a tree type structure. Based on the hierarchy, New clusters formed using the previously formed one. It is divided into agglomerative clustering, that is bottom up, top down, or cure. Clustering using representative, Birch, cure, Birch, these are the various commercial agglomerative clusterings available. They are basically using agglomerative or divisive. Agglomerative means when you have your clusters formed, then it can be either top down or bottom up approach. So, either you are joining these two which are very closer, then these may be farther, then they may be joined later. So, finally bottom to top, the closer points are brought together and they are joined and forming one tree like structure. Opposite to that is divisive, wherein you have the whole cluster and then you divide it into maybe two cluster, then that two cluster may be further divided into further two cluster or three clusters. So, top to bottom or bottom to up. So, we have an example of agglomerative clustering, bottom to up approach in our upcoming slides, but top to bottom is when you have the whole of the cluster and dividing it into sub clusters. Here you have your sub clusters and depending upon the distances, distance measures, you combine it to form a hierarchy. This is hierarchical clustering. Then we have partition clustering, Clara, K-means clustering. We have an example for K-means as well, wherein we decide how many clusters we want to form. This K is which needs to be found based on elbow methods. We will discuss this also. What is the relation of how do we find K-means through elbow methods? K-means and Clara, they are all basically based on partitioning methods, wherein you are dividing whole of the data set into certain partitions based on their closeness to each other. So, K-means clustering, Claras, these are basic example of partitioning methods. Then we have the last is grid based method. These are string and click methods. This method, the data space is formulated into finite number of cells that form a grid like structure, and all the clustering operations done on this grid only. So, some whole of the data set, suppose this is the data set and the whole grid is formed, and based on that the clustering is being done. So, let us move fast. So, what are the basic clustering methods? Partitioning, hierarchical, density. Good example of density is DB scan, optics, TenQ, and then hierarchical is agglomerative, Birch, divisive. All this we have done. Partitioning, string, Clara method. I have a numerical that we will do with the K-means clustering and agglomerative. Based on this, we will do some examples. So, let me again, I will be handling agglomerative. If you say hierarchical clustering can be partition based, hierarchy based, density based, that we have talked. Again, in hierarchical, if you dive into, then it can be agglomerative or divisive, that is top to bottom, bottom to up approach. Again, in agglomerative, we can divide it into single, complete, or average clustering. So, examples, commercial examples of these this algorithm is Birch, Cure, Rock, Chameleon. Partitioning based is distance based, model based, density based. Again, commercial example are K-means, Spam, Clara, Clarence, FCM, DB scan, click, that we have talked about. They are distance based is error square based, and then this is probabilistic model. So, we will do, if time permits, then we will do K-means and single agglomerative clustering with then examples. So, let us see what is K-means clustering. K-means means into how many clusters you want the whole of the data set to be divided. This K has to be decided very strategically based on something called elbow method. Elbow method. We will see elbow method. It will give us the point where K gives the optimal result. What is K? K is the number of clusters that we want to find out of this data sets. This is whole data set. So, how many clusters we want to find? Initially, we move with either 1, 3, 5, not once, usually 5, 3, 7. This is how we move with the random clusters. Even 1, 2 can be, but it depends on the data and its distribution. So, a hell lot of derivation has got into finding this K through elbow method. We will not get into that, but as of now, let us assume that we initially take k as a random number. In what is that k? That says how many subgroups we want to form. So, number of groups is k and the set of observation is x. Means set of observation that we have is x. See, these are set of observations we are representing with x, and these are my k, right. Distance from the observed xi to the group M center. First, randomly we select randomly we take k's value, and randomly we start with 2 centroids. If say suppose k is taken as 2, then we start with 2 centroids, and that centroid is taken randomly initially. After that, all shifting is done after checking the distance of each element from that centroid that we have assumed, and then grouping is done. And how long do we iteratively do this process? Till there is no change in centroid anymore. Okay. This is all algorithm flowchart, but we will do this with a numerical and try to understand what is the stopping point criteria, what is the stopping point of this iterations that we do to find the centroids and to find the subclusters. Right, this is a basic algorithm, but let's fast move towards the numerical that we want to talk about. So, suppose we are given with some examples where we have to where we have one dimensional data set, good enough. They can be 2 or 3 dimensional data set given in your numerical. That will make the calculations more complex, but the basic logic will remain same. Whether we are given 1 dimensional data, 2 dimensional data, 3 dimensional data, we have to basically apply Euclidean distances and some average formulas. So, Euclidean distance or simple distance, or there are n number of distance formula that we can apply. Then we can apply Euclidean distance, simple distances and many more, but in this numerical we are taking simple distance, Euclidean distance, right. We will apply k means on the following 1 dimensional data set where we have assumed k is as 2. This k, if you get a numerical, you will get the value of k, and if you do not get the value of k, then you assume that I am starting with k as 2 or 3, whatever you wish, and then you start with your iteration process. So, in the given question, we have the data set 2, 4, 10. This is the data set that we have got, right. This is my data set and this is my value of k. So, k is 2 means whatever be this data set has to be distributed into 2 partitions, right, because it is partition based that we just saw, that is k means is a partition based clustering. Similarly, hierarchical agglomerative clustering HOC, the next example that we may take is a hierarchical based clustering. So, in this one, suppose we have started with k is equal to 2. So, we have 2 centroids initially taken, C1 and C2. So, initially supposedly randomly we have taken say 4 and 11. We could have taken any 2 data set as the initial point, seed value point, as the initial centroid value, right. In this case, supposingly we have taken 4 and 11 as our initial data set, initial centroid. So, my initial centroid C1 is 4 and C2 is 11. This is first. In my first iteration, how do we start? Now, we start finding the distance of each element from this centroid that we have assumed. So, 4 minus 2, what do we see? If we want to put in C1 or C2, we will pick up each element and see whether it will go in C1 or C2. Why C1, C2? Because 2 is the one, k is 2 we have taken. So, now we have the data set 2. 2 is closer to 4 or 2 is closer to 11. How do we find? Just normal distance or Euclidean distance, whatever be the distance formula. So, 4 minus 2, 2 is no doubt closer to 4. So, it will come in this group. 4 is already there, okay, 10, and now we have to check for 10. So, 10 minus 4 gives us 6 and 11 minus 4 gives us 7. So, no doubt 10 is also closer to C1. So, 10 will come over here. 12, What about, let's check for the 12. 12 minus 4 and 12 minus 11. No doubt 12 will come over this side because of the distance. Then 3. 3 will go at what place? At C1 or C2, in the group of C1 or C2. So 3 will 3 minus 4 is 1 and 3 minus 11 is much more than 1. So 3 will come in this group. Now let's pick 20. 20 and 11. What are we doing? We are basically finding, we have taken initial C1, C2 centroid, a random centroid, and then we are trying to group all the data set in either of these groups. So 20 minus 11 and 20 minus 4, which is the shortest distance? No doubt 20 will come in this point, 30 minus 11 and 30 minus 4. 30 will come this side, and 25 minus 4 and 25 minus 11. So 25 will come in this side. So we form a whole lot of this cluster in my iteration 1. In iteration 1, we have these clusters formed. What is the next step? We have to find the average of it, an average of this centroid. To find, this is because 4 and 11 was taken very randomly. So we cannot be sure that yes, it is going to be the centroid. Centroid means center of all the data points. So now we have to calculate it. And how do we calculate it? We find the average of these elements. So 2 plus 3 plus 10 plus 4. That I've already calculated. I guess 10 will come this side. It was my mistake. 10 and 11. Let's check for 10. 11 minus 10 and 4 minus 10. Or 10 minus 4. So this is 1 and this is 6. So 10 will come this side. So I'm wrong over here. 10 will come this side. So what all elements we have in C1 and what all elements we have in C2 is, C1 will have 2, 3, 4 and C2 will have 10, 12, 20, 30 and 25. Yeah, this is the cluster we are getting, right? Now we have to find its average to find the actual centroid as of now. So how do we find average? 2 plus 3 plus 4, that gives us 9 divided by 3, that gives us 3. That gives us 3. Similarly, average of this, 10 plus 12 plus 11 plus just average. You can also find it on your own. The average of this being 108 by 6, that gives us 18. Okay. That is the way we go about in finding the, this is the outcome of the first iteration. See, this is the outcome of the first iteration that I was talking about. Initially, we take 4 and 11 as initial centroid, right? After that, we can see that the above table 2 data points are added to the cluster C1 and C2. Now we pick up whole of the data set and compare whether the new elements will be belonging to C1 or C2, right? So we saw in this that C1 will get 2, 4 it is out there, 2 and 3 in its group because of, and C2 will get 10, 20, 30, 11 it's already there, 25 in its group. What is the next step? Its average. Why do we find its average? We found its average to be how much? We found its average to be 3 and average of this was found to be 18. So this is what is happening. What are we finding? We are finding new C1 and we started with a random number, so we cannot just keep that as a final C1, C2. So our new C1 and C2 are 3 and 18, right? This is the end result of my first iteration. But we cannot stop. When do we stop? Stopping criteria is when we are sure that there is no change in centroid and no change in grouping, right? So this set, if this set is not changing, So we have, after first iteration, what do we get? Our new C1 being 3 and our new C2 being 18. So what next? What next is, again we'll have to do that iteration, that our initial data set, which is of 2, 4, 10, 12, 30, 20, the initial data set, are they displacing themselves? So let us check. So what do we see? For 2 is compared with 3 and 2 with 18. We will find that 2 is closer. Then 4 is no doubt over here only, 3 over here only. Then we have 10. 10 is closer to 18 or 10 is closer to 3. What do we find? 10 minus 3 is 7 and 10 minus 18 is 8. So it is closer to this group, C1. Similarly for 12, 12 will be closer to 3 or 18. 12 will be closer to this one. Similarly 20, 20 will be closer to 3 or 18, 18. 30 will be closer to 18 or 3. 11 will be closer to, obviously, 11 and 18. Then we have 11 this side and 25 and 18. 25 and 3 we compare, we get that 25 is over here. So we see that there is shift in the elements. C10, which was initially part of C2, is now part of C1. So this shift encourages us to go for next iteration, because there is still shifting happening between among the elements because of the change of the centroid. So 10, which was earlier part of C2, is now part of C1, and we have got the new set of elements after our next iteration. What do we do next? We again find the average. 2 plus 4 plus 3 plus 10. This new average gives us 19 divided by 4, that gives us 4.75. 4.75 is our new average of C1, and 12 plus 18, 12 plus 18 plus, again we are just finding average, you can do it on your own, divided by 5 gives us 19.6. So our new centroid is 4.75 and 19.6, right? So let's see the same. This is my shifting done. You can see this shifting is done over here, and 10, which was earlier part of C2, is now part of C1. New cluster that is formed, and found the average as 4.75 and 19.6, right? Again we do the clustering. How do we do the clustering again? Check for each element again. So the let's check for 2 is closer to 4.75 or 19.6. No doubt 2 is still closer to C1. 3 is still closer. 4 is still closer to 4.75, and 10. 10 is closer to 4.75. 10 is closer to 4.75. So we get 10 over here. And then let's check for rest of the elements. 12. So now we compare 12 with whether it is closer to 4.75 or 12 is closer to 19.6. So we will see that 12 is closer to C1. This is our new C1 and new C2 that has formed. New C1 and new C2 that has come. So 12 is closer to C1 means again 12 is coming to C1. You can see that earlier it was a part of 12 was part of C2, but now it is a part of C1, right? Let's pick 20. 20 is closer to 4.75 or 19.6. No doubt the same, it belongs to the same group still. 20 is still in the same group, 30 is still in the same group. What about 11? 11 when compared to 4.75 and 11 when compared to 9.6 has a shorter distance or is closer to C1. So that is why 11 has shifted. So we see here 11 was in C2, but now it is a part of C1. So we see that there is still shifting and change of parties are going on. And so we'll have to do this iteration till there is stability in this change of parties. So 25 is the next element that we have. 25 is no doubt closer to 19.6 as compared to 4.75. So 25 is a part of this. So we can see this change, that there is still shifting going on from this central C1 C2 to this C1 C2, new C1 C2. So we'll have to go for next iteration again. So what do we do again? We find the average of these elements and find our new centroid. So the average of these elements will give us how much? 2 plus 3 plus 4 plus 10 plus 11 plus 12 divided by 6 will give us 7 finally, and 20 plus 30 plus 25, 75 divided by again 3 will give us 25. So our new centroid is coming again as 7 and 25, right? 25. Right. Abhi tak still we are, there is a change of party happening. So we will again go for next iteration and find 7 and 25, and according to 7 and 25 now we will find our clusters. Now let's start again. 2 and 7. If you compare 7 and 7, a distance between 7, 2 and 25, 2, no doubt 2 will come in this party only. 3 and 7, 3 and 25, no doubt 3 will come in this party only. 4 and 7, 4 and 25, no doubt 4 will come in this party only. 10 and 7, 10 and 25, 10 will come in this party only. 12 and 7, 12 and 25, 12 will come in this party only. 11 and 7, 11 and 25, 11 will come in this party only. Now 20 and 25, 20 and 7, 20 will come in this party. 30 when compared with 7 and 30 when compared with 25 will come in this party only. 25 is already there. So what do we see? Now we see that there is stability. There is no change of party, no change of group, no change of shifting of centroid, no shifting of centroid at per the distance, no shifting of the whole of the set. So there is the same repetition happening with our centroid being 7 and 25 and our elements not shifting anymore. So how do we find the result? The final result is that we have found 2 centroids, 2 clusters, one having data points 2, 3, 4, 10 and 12 and 11. We are not shifting, we are not doing next iteration anymore because that is the stoppage criteria, that is the stopping criteria when the elements have started stopped shifting. And what is our C2? What are the clusters formed within? Second cluster is consists of which all elements? 20, 30 and 25. So our 2 clusters, that K was given as 2, so we formed 2 clusters. Had the K been given as 3, then we would have formed 3 clusters. Had the K been given 4, we would have formed 4 clusters. Whatever be the K value given, we divide whole of the data set into that number of clusters. Iteratively doing what? First finding the distance from all the elements with the centroid that we have assumed initially as a random number, random centroid, and after shifting and grouping it again. In that process, we find the average at each instance. So we have found 2 clusters with these data points lying together, these lying very closely to each other, these lying very closely to each other, but very far apart from each other. So what is the optimal function that we can form out of this? Optimal function that we can form out of this is, this is my final clusters. You can see we have formed this stopping criteria, and as we can see that the data points of the cluster C1 C2 iteration 3 are same as the data points of the clusters in C1 C2 of iteration. It means that one of the data points has moved to the other clusters. Also the mean centroid of these clusters is constant. The moment we find this, it becomes the stopping condition for our algorithm. Good enough. This is what we wanted and that is what we have done. And then we have how to find this k. What is the purpose of how do we find the k, that when is the k optimal? This is an elbow method that gives us the point where the minimum, the point where it is changing its angle, that is considered to be the optimal k point. So, elbow method gives us a value of k, that is a lot of proving has been done behind this elbow method. We need not get into that, but it gives us the idea of what should be the k value of k initially that we should start consider. So, that was end of k-means clustering. We will move towards hierarchical clustering, that is talking about that I have talked about is linkage, single linkage or complete linkage. How do we go about it? As we have already said, it is going to be either bottom to top clustering, bottom to top they are forming a tree, or top to bottom. Hierarchical clustering can be either single linkage or complete linkage. We will see. Single linkage means when we are finding the minimum distance between the 2 points. That is case of single linkage, and complete linkage is when we are trying to find the maximum distance between the 2. That is the case of complete linkage. So, what should be the algorithm we will discuss, but before that, k-means clustering, what we were discussing, we have discussed k, we have what should be the optimal function that I was trying to discuss. What should be the optimal function for the k-means clustering? The optimal function says that each of the element within the cluster should have what? Minimum distance between them. All the elements within the cluster should have minimum distance between them, and the centroid or the data points across the cluster should have maximum distance between them. And this is how your k elbow method has been derived from distance within the clusters and distance across the clusters. So, what should be the optimal function? That the distance within the cluster should be minimum, so that it is a well formed cluster, and the distance between the 2 clusters should be maximum. The centroid's value should be maximum, so that these points are easily differentiable from each other. So, that is the optimal function, and that is the logic, and that is the formula that has been used to find the elbow methods, k of the elbow methods, k through the elbow methods, complete linkage and single linkage. We will continue with hierarchical clustering in our next class. Thank you.